Anand in the comments, he basically asked, um, it he was basically saying if he got a dice and just shook it in a cup, put it down, but didn't look at it, that's sort of a macro analogy for what Schrodinger's cat is, right? You don't know what it is under there, and so it's only when you look up that. So what would be the difference
Right.
that something like a dice being shaken
Yeah.
to the Schrodinger's cat?
The basis is actually very different. Maybe make it easier by just using a coin toss as an example. We toss a coin and there's a 50-50 probability it will land heads or tails. That's a classical probability derived from our ignorance. So the coin will persist to have a head side and a tail side as it spins through the air. And we're just ignorant of which side up is going to be, visible when the coin lands. So probability effectively is our way of combating that ignorance by not being able to predict whether it's going to land tail side up or head side up. And we call that a probability. Quantum probability is very different. And the only way I can give you an analogy is to say that when you toss a quantum coin, it's though heads and tails don't actually exist until the coin lands and you make a measurement. So although that sounds as though you should end up at the same place, and indeed the quantum probability for a quantum coin would be 50-50, but the basis of it is very, very different. And in Schrodinger's cat paradox, what Schrodinger was doing, this is very tongue-in-cheek, it was dismissed literally a couple of sentences in a review article published in 1935. But the point that Schrodinger was making is saying, look, this is ridiculous. This is absurd. This cat can't be both alive and dead. Something's gone wrong. Something is missing from the quantum formalism, from the equations of quantum mechanics. There ought to be some line in the equation that says, no, this comes out somewhere. And we know the answer before we lift the lid and look. The fact of the matter is, though, it's not in the equations of quantum mechanics, and therefore, arguably, it's a question as to where you want to draw the line. There's good arguments to say, well, superposition states like these ones that I've been talking about are actually so extraordinarily difficult to maintain. They suffer from something called decoherence. That any attempt to try and see a superposition of an alive and dead cat, forget it. I mean, the superposition is not going to survive to classical scales. It's all going to be long gone by the time we've cranked up the measurement chain all the way to a macroscopic object. But again, it's debatable. If you want to take an anti-realist interpretation, then yeah, the superposition is a simple statement of our state of knowledge. It could be dead, it could be alive. It's one or the other. We don't know, though, until we lift the lid of the box and look.
So we've had a few questions on Schrodinger, which I'll just get to in a second. I forgot to mention at the start of the Q&A, we had someone called, we have a lot of viewers from India. It's the third biggest country who watches these streams. So hello to everyone in India, because it must be getting pretty late in India now. So well done for staying up. But we had someone called Amy Beattie who said she was watching from Australia at 4 a.m. So if you're still awake at 5:15 in the morning, Amy, let us know. But anyway, so this is a question that is either really, really clever or just sounds really clever and is actually dumb. So Tom Thatcher asks, Schrodinger and the box are both in a bigger box. That box doesn't open until Schrodinger has opened the smaller box and seen the state of the cat. How do we describe Schrodinger's state prior to the box opening, and how many iterations of box and observer can we fit around it? So could you have like nested Schrodinger's cats?
Well, there are parallels with another paradox that I haven't mentioned this evening called the paradox of Wigner's friend. And it is related to the idea as to whether or not there's a role for human consciousness in this whole process, in this process of quantum measurement. Wigner set up a hypothetical example where he had a friend in the laboratory make a measurement, let's say spin up, spin down, it's one or the other, and the friend sees spin up, records it in her laboratory notebook, and outside in the corridor, Wigner would still describe the physical state of the object, whatever it was, as a superposition. It's both. It's a mixture of those. So he goes into the lab and he asks his friend, "Oh, what did you see?" And she says, "I saw spin up." Okay. For Wigner, the wave function collapses at that point. But then he asks her again, but are you sure you saw spin up? She gets a bit frustrated and says, well, of course I did. What's the matter with you? And Wigner realizes, in fact, that to assume that the wave function collapses when it encounters his consciousness means that his friend was in some kind of state of suspended animation, aware of both opportunities. So the conclusion from that paradox was that it must collapse when it encounters the first conscious mind. And if you want to answer the question of the nested box scenario, there are certain philosophers of consciousness who would argue that cats have a degree of consciousness. And if consciousness is all it takes to collapse the wave function, then arguably the cat itself it collapses itself into a state of being alive, yay, or a state of being dead.
So I guess that answers Ella Greensmith's question of would it be possible for two different observers to observe different wave functions for one electron if they kind of both open the box at the same time and looked at it? Could it collapse? Yeah, that wouldn't happen, is what you're saying. And also, Naomi Dubois also asks a seemingly simple question, but I think it's one that you're going to definitely say no to, but other philosophers would say yes to, which is the cat alive in one universe and dead in a parallel one?
Well, according to those who advocate the so-called many worlds, who want to take a rather extreme view of the universe splitting, I mean, the first thing that I should say is, although I don't like this interpretation at all, I acknowledge in the book that it's truly remarkable that the simplest solution to this conundrum in a realist interpretation of quantum mechanics leads us to this place. The idea that the universe is constant. In one universe, Gwyneth Paltrow got on the tube and had one kind of life, and in another universe, Gwyneth Paltrow didn't make it on the tube and had a very different kind of life. For those of you who are familiar with the film Sliding Doors, and that's the kind of logic. So the answer is yes. This is what the many worlds interpretation would suggest. However, there are lots of issues with it that make it uncomfortable. Not just philosophical issues. There are, I think, genuine scientific issues of how you get back to some of the things that quantum mechanics predicts from something like a many worlds interpretation. You have to have a very elaborate mechanism to explain quantum probability, for example. And I'm not saying right or wrong. I'm just saying for me, it's overwhelmed by its metaphysical content. It's too full of an idea that can never be proven. You can't prove that the cat is dead in this other universe because you can't access that other universe.
So we had a few questions about entanglement, actually. So Gavin Meerwald asks, can entanglement exist between more than two particles? And if it does, what would the collapse of those particles look like?
Yeah, it can absolutely. In fact, there were some very, very neat experiments done about 20 years ago, also involving Anton Zeilinger, involving entangled triplets of photons. So three photons entangled. All you need to do to create entanglement is to create a situation where either two or more particles are emitted, where their properties are obliged to be correlated according to the laws of physics, usually a law of conservation, maybe of angular momentum, energy, whatever it might be. And these experiments on triplets of photons were fantastic because they allowed laboratory tests of so-called local realism, but without recourse to Bell's inequality. They didn't need to use Bell's inequality to show that, in fact, again, quantum mechanics predicts the right probabilities. Any assumption that these triplets of photons were already pre-existing in fixed states at the moment they were created gave the wrong probabilities. So again, the results were unequivocal. But absolutely, you can, I've no doubt, create entanglement with n particles, where n is quite a large number. But be aware that creating entanglement, these superpositions of entangled particles, are extraordinarily delicate. They often rely on high power laser equipment. They rely on being shielded from the environment. What you need to avoid, in fact, of course, the basis of quantum computing relies on entanglement, and this is why we don't yet have, a quantum computer sitting on my desk here in my study. There are quantum computers, but the number of qubits, the number of entangled things involved, are still in the very low numbers.
Actually, Derek Thorpe asked a question about that. So he said, "How has quantum physics enabled modern computing?" And as like you say, we don't have a quantum computer sitting on a desk, but quantum effects and quantum physics is used
Well,
all the time to create circuit boards and stuff. Surely.
you manipulate design semiconductors on the basis of using quantum mechanics. Now, that just means using what I'd call ordinary quantum mechanics, not the kind of spooky stuff we've been spending the evening talking about here. But it is the fundamental description that we use for all molecular, atomic, and subatomic particles. Semiconductor electronics. I mean, even what we're doing right now this evening. You think about the electrons passing through your computer, streaming live from the RI or streaming from my study at the very least. All depends on quantum mechanics to a greater or lesser extent. It underlies and underpins everything about what we regard as modern technology.
So Anand asked a kind of fun question, which was, what is the largest particle that shows wave-like behavior? Now, as far as my A-level physics is concerned, you can actually just work out a wave function for like a supertanker if you want. It
Yeah.
just won't be very big. So is that what's the kind of largest particle where it's practical, I guess, to have a wave function?
What's interesting, and this is a very, very legitimate question. What's interesting is the extent to which you can push, perhaps not macroscopic objects like cats, but what's known as mesoscopic objects. So tiny. A good example is so-called superconducting quantum interference devices.
We have one in the basement of the Royal Institution.
Or SQUIDs for short. Okay, superconducting quantum interference devices. In effect, it's possible to create a superposition of electrons, superconducting electrons, going one way and another way, and these are of dimensions that are visible to the naked eye. Okay, so it is possible. Again, very, very carefully. You've got to be aware of environmental decoherence and other things, or you can't preserve the superposition. Now, for me, a superposition is evidence of wave-like behavior, if you want to think about it like that. There is a bid to create a satellite mission called the Macro mission, MAQRO, if you want to Google it, which would put some small nanospheres into orbit and look at quantum interference between these spheres as a way of, again, trying to determine, what kind of realist interpretation might still be legitimate. The view being that if we're going to penetrate to a deeper level, if there are deeper principles, then we've really got to come up with some very, very clever experimental arrangements if we're going to do that.
So you'd obviously expect this question to come up. We've had a few people ask it as well. So Garth Wilkinson, Nick Brown both asked, since quantum theory has not been reconciled with general relativity, is it likely that it's not complete? And what's the current position on a quantum theory of gravity?
Depends who you talk to, and depends what books you read. So the answer is absolutely. One of the pieces of evidence that I would use to argue that quantum mechanics isn't finished yet is the fact that the way that we use space and time in quantum mechanics, so fixing it with special relativity is not a problem. Dirac did that back in 1928. But space and time in quantum mechanics is not so very different from space and time in classical mechanics. As the guys asking the question know, general relativity, space-time is very different. It's a dynamic, it's the result of the action of energy and mass creating, effectively, a dynamic space-time. Now, bringing these theories together to produce a quantum theory of gravity has proved extraordinarily difficult. There was a lot of fuss about the possibility that string theory might be the answer already some years ago, because it seemed to predict a particle called the graviton, which is the notional force carrier of the gravitational field. There's another theory that I wrote about in quantum space called loop quantum gravity, which takes another route towards quantizing general relativity, basically. And that predicts in effect that space itself is quantum in nature. There are literally lumps, quanta of space, area and volume. So these are fascinating, but they're very speculative. There's no evidence at the moment, one way or another. And I won't say it's hopeless or futile. Far from it. There are some very, very clever folks working in these areas, but it's tough. And it's difficult right now to see how we might get to a situation where either of these approaches could even be remotely put to the test.
Well, that was going to lead into my next question, actually. So both Ian Hooper and Sanjit Raman were both asking, can you envisage any experiments which will be able to settle which of the interpretation of quantum mechanics is correct? And how do you set up a test or an experiment to test, say, a final theory of quantum gravity?
What I found really quite interesting as I was writing Quantum Reality is the realization that I actually put a fourth proposition into the book, which I haven't talked about tonight. What's interesting is that if you look at anti-realist interpretations like the Copenhagen interpretation and relational quantum mechanics and cubism and others, these theories effectively say, okay, that's it, folks. Just don't look. It's like a emergency personnel at the scene of a tragic accident. They say, move along, there's nothing to see here. So there's nothing more to see. And I don't know about you, but that's not very motivating to an experimentalist who wants to find deeper principles that explain the entirety of nature. It's funny, it's the realist interpretations that are more active. They encourage experimentalists to say, oh, well, we can build an experiment to test that. If you want to have a physical collapse mechanism, then yeah, well, why don't we look for it? And so they build an experiment to look for it. I'm not very optimistic about how far we'll get. I mentioned the macro mission. If that ever gets off the ground in a decade or so, it might be interesting to see what that produces. But I think it goes against the grain of human nature not to try to keep looking. In the meantime, what we've got is philosophical questions for which there are endless answers one way or another. You choose which horse to back. Do you want an anti-realist interpretation? Do you want a realist interpretation? If you're going to put hand on heart and say, I want to know more about how nature works, then you're more often than not likely to be choosing a realist interpretation. Then you just got to decide which horse to back.
So we've had so many great questions, and sorry to everyone out there who hasn't had a chance to get their question answered. But I just wanted to finish on this one because it's quite a nice one, and it's not about quantum, so I think you probably appreciate that. So Kash Wadwa says, as a science writer, what do you regularly read or do to make sure you're keeping up with all the latest developments across science?
I don't try.
It's good.
So that needs an unpacking, doesn't it? I don't try because there's way too much. There'd be way too much to read. It's funny. It's like when I used to be an academic, and my attitude to keeping up with my own scientific discipline was to go to the library on a regular basis, spot an article that looked interesting, photocopy it, and put it in my filing cabinet. I never looked at it. But I was happy that I got the article in my filing cabinet and it was there to refer to if I ever needed it. And it's a little bit like that with the whole slew of papers published on the archive, papers published in the scientific literature, papers published in the popular literature, magazines like Quanta. If I tried to read everything, I'm actually interested, unfortunately, just as an individual, in too many things. I would. So what I do is I do differently. When I had an idea for a book, or there's a theme, or I'm developing an idea and I want to write a book proposal for a publisher, then I research. Then I'm digging into the literature that's just relevant to the area that I want to write about. And so I play catch up as best I can. In the case of quantum mechanics, I've been fascinated by quantum mechanics for 30 odd years. So I know a lot, but there's still a lot of developments happening all over the world that are important to a certain extent stay on top of, even if only somewhat superficially, because I think I know enough that I can pick up very quickly what a new paper might tell me where they've studied this collapse mechanism, and they've come up with these results or whatever it might be. But that's what I try and do. I'm not an academic scientist. It's not my livelihood to stay on top of the scientific literature. I'm a writer. Once I've got an idea, or I've got an idea for a proposal, I then will dig into the literature and research it as best I can.